Okay, so good afternoon everyone. Welcome to the second lecture of LP&CO. Are there any questions or concerns before we get started with basic graphs here? Anything to ask? Anybody who joined late and has any questions or otherwise? No? All good? Okay, so let's continue our journey through basic graph theory. I mean, it's kind of silly to call it graph theory. We call it graph theory terminology because that's what it is. Right, so here's another example, slightly different from what I did last time. And you can draw this differently. There are two drawings of the same graph. You have four vertices and you have an edge joining any two vertices, right? So in that sense, graph is an abstract mathematical object. And by that I mean, as I mentioned last time, it may have different representations. Such as drawings. You see two drawings of the same graph here. It may also have other representations such as adjacencies and matrices. We'll talk about these later, in case you haven't seen them before. Okay, and more formally, or more precisely maybe, it has two things: the set of vertices and the set of edges. And each edge may be viewed as a pair of unordered distinct vertices. Pair of unordered. That's all. So therefore, in this course, when I say graph, generally speaking, unless otherwise specified, I mean a simple, finite, undirected graph. Right? Finite means finite, number of vertices, number of edges are finite. Undirected means there are no direction on the edges. There is a thing called directed graphs where you have a direction for each edge. We may encounter these, but in general, when I say graph, I mean undirected. And finally, simple means we don't allow loops. Loops are these, and we don't allow parallel edges or vertical edges. If we do allow, I will mention that explicitly. Right? Okay, so that's all we discussed last time. I want to introduce some more terminology. Let's go more interesting example. Let's say, I don't know. Here is a graph. For this example, this is my graph G. And let me label the vertices 0, 1, 2, 3, 4. And let me also label the edges E1, E2, E3, E4, E5. Number of vertices equal to number of edges, 5 equal to 5. I don't like that. I'll put one more edge and I'll call it V6. So here's a graph with 5 vertices and 6 edges. And let's talk about some terms you already know. but I want to make sure that we are all on the same page, right? So when I use a term, everybody should know exactly what I mean. So let's talk about adjacency. So, I'm not a big fan of writing down definitions because you all can write them on your own. So I'll define most things through examples. If there's any confusion, let me know. And you should be able to write down the definition yourself. So, can you give me a pair of vertices that you think are adjacent or should be called adjacent? Anybody? Yeah? 0 and 1 should be called adjacent. So we will call them adjacent. 0 and 1 are adjacent. And somebody else, give me a pair of vertices that you think should not be adjacent. Huh? 1 and 3. 1 and 3 should not be adjacent, therefore they are not adjacent. So we have defined adjacent and non-adjacent. Right? Two vertices are adjacent if there is an edge joining the two vertices. Joining. E1 joins. Please don't use connects. Connects has many other meanings. E1 joins blah and blah. Blah and blah. Somebody? 0 and 1. E1 joins 0 and 1. So that's what I mean by joins. I may also say 0 and 1 are the ends of E1. 0 and 1 are the ends of E1. Some people say end points, it's unnecessary, ends. Right? Okay? So we understand what ends of an edge are, we understand what it means for an edge to join two vertices. And if an edge joins two vertices, then those two vertices are adjacent. And otherwise, the two vertices are not adjacent. Everybody with me? Okay. But we're going to use the word adjacent. You're going to overlook it. Right? You're going to use it in a different context also. Can anybody tell me another context in which I can use adjacent? I can use it for two vertices. Two edges. We'll go with two edges. So can somebody give me a pair of edges that are adjacent? Raise your hand. Two edges that are adjacent. Okay. So John? E4 and E6 are adjacent. E4 and E6 are adjacent. Okay, so we'll call them adjacent. Non-adjacent example? Anyone? Yeah.
E1 and E6.
E1 and E6 are non-adjacent. Okay. Yeah? So everybody gets it? Two edges are adjacent if they have a common vertex. If they are both sharing a common vertex. It would be nice to have a term for this. Okay? I wanted to use a term, but I did not have it. So let's talk about that. Anybody? We talked about vertex and vertex. We talked about edge and edge. Anything else you can think of? Yeah. What's the other combination? Incidence. For vertex and edge. Let's talk about incidence. Can somebody give me an example of a vertex and an edge that are incident with each other? Yeah? 0 and E1. I can say E1 is incident at with whatever at 0. Or I might just say 0 and E1 are incident. I personally prefer this, but I guess I think both are okay. 0 and E1 incident with each other. That's common, but why not? Yeah?
So without direction, how?
Sorry?
Without direction.
Right. Okay, so you tell me. Can you give me a vertex and an edge that are not incident? And then you will talk about direction, whether they play a role or not. So can you try to give me an example of a vertex and an edge that are not incident with each other? Of course, I have not defined it. I'm just asking you to guess. Yeah?
You don't define it.
Yeah, what is it? Can you give me an example? Just guess. What do you think is an example of a vertex and an edge that are not incident with each other?
E2 and 4.
E2 and 4. E2 is not incident at 4. Yeah? So now can you tell me what is the definition of incidence? It just works, right? So,
Yes. And
right, exactly. You'll say that an edge E is incident at a vertex V if V is an end of it, right? So we don't need directions. Of course, when you have directed graphs, you can talk about that also. But yeah, without direction also, you can talk about a vertex and an edge being incident or not. The point is, so this is not just about graph theory. In any area of mathematics, or maybe other areas of life, I don't know, you will see the words adjacency and incident being used. Adjacency is typically used when you are talking about objects of the same type, vertex and vertex, edge and edge. Incidence is typically used when you are referring to objects of different types. Vertex and edge typically use incidence. Right. So there are other areas also where you will see such things. Right. Okay, good. Some notation. We will find it useful to talk about all the edges incident at a vertex. Yeah, all the edges that are incident at a particular vertex. So, we will use partial of V as the set of edges incident at the vertex V. Also, please don't use E, F for vertices and don't use U, V for edges. Please, that's a crime. It should be prohibited, right? So for vertices, I generally suggest use the last letters of the alphabet, S to Z. There's enough alphabets there. If you really need, you can go with subscripts and superscripts. And for edges, I suggest you stick to D, E, F, G, H. In fact, G and H also I like to avoid because of that for reserved for graphs. D, E, F, that should be enough, right? And your subscripts and superscripts. So please use notation that is intuitive and don't mess with our brains when we are marking your assignments, right? You don't need to do that. So, partial of V is a set of edges incident at a vertex V. I will write V, D, X, or V. Please don't do that on my assignments. In your macros, you can create a macro. Right? I cannot create a macro on the board. So, okay. So this is the set of edges incident at a vertex V. Let's go to example. Can somebody tell me what is partial of 2 in this graph? In the graph we have drawn. Partial of 2? Anyone? E2, E3, E4, E5. Okay. E2, E3, E4. Yeah. Let's move on more. Partial of 0. E1, E2, yeah. Okay. Okay. And sometimes in life, we also find it useful to talk about all the neighbors of a vertex. Right? Let's try to guess what that is. So I'll use n of v for the neighbors. This is my spelling of neighbors. I'm just going to use that of v. So can somebody tell me the neighbors of 4?
2 and 2.
2 and 3. Yeah? Neighbors of a human are typically humans. So therefore neighbors of a vertex are going to be neighbor vertices. Neighbors of 4 are, in this example, 2 and 3. So basically the vertices that are adjacent to this vertex. Yeah. Okay, so that gets us through incidence, adjacency, joining, ending, whatever. What else? LaTeX. Since you'll be using LaTeX for all assignments, this is generally partial of B. This is the LaTeX code. Okay, so if I say partial, it's eternally code. But if I do, it's because I use LaTeX all the time. So. Okay. Questions, concerns regarding any of these things? All good? Yeah? Okay. So let's continue to more interesting things in life. So, the course is called LP&CO, right? And the reason we are talking about graphs is because C, right? So we are going to talk about combinatorial optimization, and most combinatorial optimization problems are based on combinatorial objects. And in this course, it will be largely graphs. In fact, I would say graphs are perhaps the main source of combinatorial optimization problems out there. If you pick up any book on combinatorial optimization, you're likely to see a whole lot of chapters just on graph theory problems, and sometimes only on graph theory. So, because of that, we will be talking a lot about graphs, problems defined on graphs. And one such problem is related to matchings. Sometimes more specifically, maybe perfect matchings. Right? So we'll talk about matchings and perfect matchings. We will define what they are, and then we will talk about things related to that, and we'll gradually move into the LP world from it. So, example. Here's a nice graph. One of my favorite graphs for various reasons. Anyways, that's not the point. Let's count the vertices. 0, 1, 2, 3, 4, 5, P0, P1, P2, 3, P4, P5. Of course, I can just, instead of P1, I can just say 1, 2. Sometimes I can just say the edge 1, 2, because it's a simple graph. There is exactly one edge joining the two, or there is no such edge. So I can also just say edge 1, 2. But sometimes it's just convenient to label the edges, right? So even if I don't label the edges, I can still refer to the edges by the ends of the edge. Especially because we don't have multiple edges in this case. Yeah, when you have multiple edges, you kind of have to label the edges. No problem. Yeah. Okay, so here's an example. And let's talk about matchings and perfect matchings. First we'll talk about matchings. How many of you have seen matchings? Or how many of you have not seen matchings? If you haven't seen matchings, raise your hand. Just to get an idea of what level I'm pitching to pitch at. Anybody who has not seen matchings before? Okay, good, okay, good. At least a few of you, good. So that means a large number of you have seen matchings. Okay. So those of you who have seen matchings, can you give me an example of a matching in this graph? A matching. Raise your hand.
142503.
Okay. 142503. Okay, good. I forgot to label some edges. Thanks. E5, E6, E7, E8. So you mean the edges I did not do. Thank you for reminding me. Good. So that's a matching. E6, E7, E8 is an example of a matching. Yeah, I haven't defined it. I just color it. This is a matching. Okay. Anybody else? Another example? But I don't want the same size. This matching has size 3, cardinality 3. I want a matching that does not have cardinality 3. E0 and
E4.
E4. Great. E0 and E4. That's a matching. Okay? Can somebody give me an example of something that is not a matching? E0? E0, E7 is not a matching. Okay, let me just write down this one. E0, E4 is a matching. And your point is E0, E7. E0, E7. Not a matching. Look at E0 and E7. E0 is this edge, E7 is this edge. So now the ones who have not seen matching before, would you like to define a matching? What do you think is a matching? So you have seen 2 examples of matchings, and you have seen at least 1 example of not a matching. So any guesses on what a matching could be? Sorry? Louder? Similarities. Okay. What exactly do you mean by similarities? Can you explain a bit more? They are parallel. Parallel. Okay. Like in the drawing? Great. Excellent. Good. So this is exactly the kind of answer I'm looking for. The drawing of a graph has no relevance to most of the things we are defining. So whatever we are defining, so I'll give you a reason. So I could have used the words points and lines. Do you all agree? Why vertices and edges? What's the use of this fancy terminology? Right? Points and lines. You can tell anybody, right? Everybody knows points and lines. So why is it that we don't use points and lines?
What's that define length and position for one?
When you say points and lines, we think about the drawing, the way it is drawn. All of this is irrelevant. A graph is an abstract mathematical object, and almost everything we are defining in this course for a graph, it has nothing to do with how it has been drawn. In fact, we could have not drawn it at all, and I could still talk about adjacency and incidence, right? So yeah, so I'm glad you mentioned that, because yeah, for those of you who are seeing graph theory for the first time, please remember this is not geometry, right? So we don't care about how the graph is drawn, whether it is drawn or not drawn. None of this matters. The drawing is only to aid us, to help us see what's going on. Okay? So now anybody else? So whatever definition you have of matching or not a matching should not have anything to do with the drawing of the graph. That's the first point. So anybody wants to try? Somebody who has not seen matching before? Here are 2 examples of matchings. Pink is a matching, yellow is a matching, and orange, just draw it. Orange is not a matching. Orange is not a matching, pink and yellow are matchings. Any guesses? So what's the difference between the pink and the yellow versus the orange? Sorry? Okay.
They are connected.
Connected. Can you explain that? What do you mean by connected? Because we did not define it. They are joined. Can you make it more precise using terms you've already defined? Right, so whatever we defined, we have defined incidence. Adjacent. E1, E0 and E7. E0 and E7 are adjacent. E0 and E7 are adjacent. This is the problem in life. These 2 are adjacent. Right? This does not happen here. Here you pick any 2, they are non-adjacent. Any 2 are non-adjacent. Can somebody put it differently? Any 2?
They don't have any vertex.
Right. Any 2 are non-adjacent. Is there an easy way to say this? Pairwise non-adjacent. A matching is a set of pairwise non-adjacent edges. That's what a matching is. any set of pairwise non-adjacent this is what match is. Right? Pairwise they must be non-adjacent. If any two share a vertex, that is not matching. Otherwise it is matching. So now let me ask you a question. Can I add one more edge to this set and get a non-matching? Or can I add one more edge to this set and get a matching?
No matter what
No matter what edge I add, it is not matching because already I have a pair of adjacent edges, right? So not only is this not a matching, every superset of this, including itself, every superset is not matching. Every superset is not matching, right? Each superset. Each superset of the graph of this set is not a matching. And of course, the set is a superset of itself, right? Because mathematicians are silly, they like silly things. Okay, good. Questions, concerns? All good? Right, so everybody is okay with what the matching is? Okay, so here's a question. Can you give me a graph that does not have a matching?
No.
Any graph. I have not defined connected, disconnected, so we shall not use those terms. Can you give me a graph that does not have a matching?
Even anti-set is
Okay.
Three vertices and all three.
Three vertices
With three edges.
and all three edges. Good. Let's do that. Three vertices and all three edges.
Complete.
Yeah, this set, this graph?
Yeah.
Okay. So you're saying there is no matching in this graph? Yeah, you sure? Pay attention to the definition. Yeah?
Single.
Single edge is a matching. Okay? What if there is no edge in the graph?
Any complete.
Complete graph. What about them? They don't have a matching?
Because any.
But this is a complete graph. This is a complete graph. So are you saying this one does not have a matching? Has or no?
It doesn't have.
Doesn't have a matching? Okay. Why not?
So because we choose any two.
Why are you choosing two? Right? Why are you choosing two? To see my point? Why choose two? Why not choose one? Then does it have a matching? Okay. Good. And what about this graph? Does it have a matching? Right? Why?
So we don't need to choose any.
Choose nothing. Choose nothing. That is one choice in life. At least in this life. Yeah. Okay. So therefore the empty set is a matching. You all agree? The empty set is a matching of any graph. Therefore every graph has a matching. Yeah. Okay. The empty set is always a matching. Yeah. Alright. So now let's define matchings using some notation. You'll see the point of this later. So I want to define a matching again. It's the same definition. For a graph G, so G is my graph of this. M subset of the edge set of a graph is a matching if I want you to think about it, right? So don't write it out if you see it, right? I want you all to think about this because especially for some of you, the notation might be new, right? So I want you to think about this. I want you to complete the definition by doing something else here. for every vertex. If it satisfies something for every vertex, what is that thing? If you have an answer, raise your hand and I'll come and talk to you. I suggest you just write it down in your notebook. That way you don't even have to give away the answer to your neighbor. Adjacent vertex. Anybody else? Yeah. Okay. Let us think about it. Okay. Everybody got it? Alright, so everybody sees it? This has to be, the cardinality of this set has to be 0 or 1 for each vertex. You all agree? Yeah? So that's matching. Since some of you are not coming from math backgrounds or maybe even CS backgrounds, I want to have a brief discussion about this. Do you see where I'm going? Shouldn't it be if and only if? Why did I write if? Right? I claim to be a mathematician. Why did I write if? I should write if and only if now. Anybody has an answer? Somebody who is preferably not from math or CS backgrounds. Why if? Why not if and only if? Nobody? Or is everybody from math and CS backgrounds? That's interesting. Why if? Why not if and only if? Okay? Maybe CS allowed, maths is not allowed. Okay?
Because it's a definition.
It's a definition. Mathematicians are humans. When they define, they use if to mean if and only if. I shall take the umbrella if it's raining. Generally speaking, when humans say this, they mean if and only if. If it's not raining, I'm probably not taking the umbrella. That's what it is. That's typically what you would interpret it. Right? So, if you are reading a book or something, if you see a definition, if means if and only if. Right? And the reason this is the definition is because I put a box here. If I put a box, it's a definition. Or if I underline, it's a definition. Yeah? Okay, good. Yeah, in a theorem I would not say it. In a theorem, I wouldn't say if to mean if and only if. In a theorem, if I say if, I really mean if. Oh, okay. So that's what matching is. Now let's go back to this example. You see some matchings. You have listed down 2 matchings. There are more matchings. What do you think is a perfect matching? What do you think is a perfect matching?
The vertices are covered.
All the vertices are covered. Every vertex is matched to somebody else. Exactly. So, how shall I change this to make it definition of perfect matching?
Equal to 1.
Equal to 1 for every vertex, yeah? So if I want to make it definition of perfect matching, then I will simply put equal to 1 instead of whatever this is. Yeah? So if every vertex has been matched to another vertex, such a matching is called a perfect matching. Yeah? So in this example, do you all agree that the pink one is a perfect matching? Yeah. Pink one is a perfect matching. And I shall abbreviate perfect matching to PM. Yeah. Good. We discussed that every graph is a matching. Does every graph have a perfect matching? Yeah? No? How many of you think yes? Does every graph have a perfect matching? How many of you think yes? No? How many of you think no? Okay, everybody? Fine. So that's right. I mean, in particular, you need to have edges, unless your graph itself has no vertices and no edges. In that case, the empty set is a perfect match. But yeah, no vertices and no edges is also a graph. It's called a null graph. We will generally not talk about it. But it is a graph. I did not say those sets are non-empty. I just said they are finite. Okay, so can somebody draw a graph? Here is a quick DIY. Draw a graph. DIY means do it yourself. Some of the DIYs will be in class DIY. Draw a graph with n vertices, n equal to 4. 4 vertices. I did not talk about degree of vertex. Let's quickly talk about the degree of vertex. In that example that we drew, what do you think is the degree of 2? The degree of 2 is 4. And what do you think is the degree of every other vertex other than 2? 2. Yeah? Okay? So, degree, in that example that we have, degree of 2 is 4. And degree of, I don't know, I is 2 for all other I. Degree is the number of edges it's selected a vertex. Okay. So coming back to this DIY, I wanted to draw a graph with 4 vertices. Each vertex has degree at least 1. But the graph has no perfect match. Make a drawing in your notebook. I don't know how many answers there are to this question, but I know there is at least one answer to this question. So see if you can draw such a graph. Yeah. Q. Yeah. Yeah. Right. Yeah. Good try. Yeah. Which one? Right. That works. That works. That works. That works. That works. Yeah. Not about it, not about it. Try again. Try again. If you already found one such graph, see if you can find one more. I really don't know the answer, but literally I just made it up. Okay, so I'm not going to give you the answer. Good number of you have gotten it. Those who haven't gotten it, keep trying it. Yeah, not a big deal if you didn't get it. Okay, so the answer is yes, there is such a graph. It exists. I don't know how many. Okay, good. Right? I'll draw another graph. Maybe not the same question, but maybe I'll give you a graph on 6 vertices that doesn't have a perfect matching. You agree? Graph on 6 vertices, no perfect matching. Convince yourself that there is no perfect matching. Okay, good. So in general, a graph does not have a perfect matching. And in general, a graph may have many perfect matchings. For example, this graph that we drew earlier, we saw a pink perfect matching. Can somebody give me another perfect matching in the same graph?
E2, E7,
Okay, E2,
E7, E5.
E7, and E5. The blue perfect matching. Okay. So yeah, okay, good. So what's next? So what we are going to do next is, we are going to gradually move towards this left side. Right? And we are going to use perfect matchings and matchings as our example. So, here is a thought experiment. Some of you may have already taken courses where you have seen these things, so those people can relax. But the rest of you can focus on this, and others can also focus. What we are going to do is, we are going to introduce variables. We are going to write down a system of linear equations or inequalities. I have not told you what the variables are, but we are going to write down a system of linear equations or inequalities, so that whenever you take any solution to that system, an integral solution, or if you like, an integer solution, but all the variables are integers, that solution should somehow correspond to a perfect matching of the graph. Okay, let's see the word. We are make some more space. Let's draw the same graph again. You like this graph. Zero, one, two, three, 4, 5. Before we embark on this exercise, let's spend some more time on this graph. We saw two perfect matchings. Yeah, maybe we'll do this exercise. This is it. We saw two perfect matchings. The pink and the blue one that are drawn here. I want to actually take some time and count all the perfect matchings of this graph. Okay? So let's do this exercise. You can take this DIY for now. Here's a quick DIY. Count perfect matchings of this graph G. This is the name of G for this discussion. Yeah? I want you to count the number of perfect matchings in this graph. And I will give you one small hint, which is actually a useful concept we will use later. So I want to tell you what a cut of a graph is. Okay? What is a cut? You partition the vertices into two parts, and you look at all edges going from one part to the other part. Okay? So here is my cut, the particular cut I want to look at. The left hand side is x. X is 0, 1 and 2, these three vertices. The right hand side is the complement, 3, 4 and 5. And the cut, I will denote it as partial. Welcome again. Partial of capital X. Here you all see, this partial is almost the same as the earlier partial, but more generalized. Yeah? If you can't see it, think about it. Why are we using the notation partial? Of course, here X is a set. There we just put a single vertex. Yeah. But of course, partial of V, you would imagine this should be the same thing as this, where you put V in a set. Is partial of X kind of clear? X is a set of vertices. Partial of X is all the edges that are having one end in X and the other end is in the complement. Let's write down. So, for a graph G, any graph, take a subset of vertices, any subset, then partial of X is the set of all edges that have one end in X and other end in X complement, which is of course defined as vertices of G minus X. For any set of vertices X, I can talk about the partial of X. Such a set is called a cut. Any such set of edges is called a cut of the graph. And we will find cuts very useful in this course, like pretty much every course I teach. Such a set of edges is a cut of the graph. Yeah? So, anyways, so if you don't have to worry too much about the general definition, I want you to look at this cut. How many edges does this cut have? 3 edges. Yeah? There are 3 edges in this cut. I want you to pay attention to this cut in order to solve this exercise. Okay, think about it. And if you have something, write it down and I will come and talk. Looks like I wrote it a bit too small. One end in X and the other end in X bar, which is the complement of X. Yeah. One more point related to notation. Typically, if I want to define something, I will use colon equal to. If I use just equal to, I'm probably claiming that we have improved equality or something, right? But anyways, I generally try to be consistent, but sometimes if I am not, ask me, I'll just interpret from the context. Okay, so I want you to use this cut. This cut has 3 edges, and I want you to use that information and the structure of this graph to figure out how many perfect matchings it has. If you have figured out the number of perfect matchings is k, seeing that it is at least k is easy, but you should also convince yourself that it is no more than k, right? Which is a bit trickier generally. So, yeah.
Try to see if you can somehow use K. How do you convince somebody that something is on relation to that? How do you So what you said is correct. fine. You are it's not. Whichever one you find.
So just to clarify, we are counting number of perfect matchings, right? We are not counting number of cuts or anything. My suggestion is to count the number of perfect matchings. So there are two steps. One, you can just sit down and start counting, right? You can just exhaustively try to figure out. And most of you have figured out that the number of perfect matchings is equal to some k, right? And you believe that it is actually equal to k, right? It can't be less than k because you already found k. Okay? Assuming you did not make any mistake, it is at least k. The harder part is to convince somebody that it is no more than k. Right? Somebody will tell no, there's k plus 1. I can be one more. So how do you argue that no, there is exactly k? For that, I am suggesting you use this cut. Not the concept of cuts. This cut. Right? So this is also an exercise to become familiar with cuts because you will see a lot of cuts in this course. Right? So I also want to use this exercise to help you familiarize yourself with cuts. Okay? You can do more because I know perfect matching. What is the number of vertices in the graph that has a perfect matching? Think of like that. Yeah, any other questions, concerns? Okay, so I don't want to conclude this discussion today. I want you all to have more time to think, right? So, so what you need to do is, you need to conclude that the number of perfect matchings is at least k for some integer k, and then once you are convinced that this is the right number, I want you to think about greater than or equal to k. For this, I want you to think about the cut. Okay? What does this cut have to do with perfect matching of the graph? Right? This particular cut. Of course, you can make statements about every cut and perfect matching, but this is the cut that will help you in this graph. Another point I want to mention is, for those of you who have never seen any graph theory, please pay close attention to the definitions. Don't get misled by the drawings. Look, the drawings I make, I try to make pretty drawings so that you can visualize it. But that also has a downside, because now you can visualize it, and that can lead to incorrect interpretations of what we are doing. Right? So some of you seem a bit confused by what is a cut. What is a cut? Don't look at this example, look at this definition, and try to do more examples. Okay? And if you want to make ugly drawings of this graph and observe the same cut, that is also useful. Right? I'll give you one ugly drawing. Well, I don't know how ugly. Ugly is hard. Let's see. Now I'm looking confused. Same thing. Okay? It's ugly in the sense that it has too many edges crossing, but it's still kind of pretty. So, okay, good. So that's all for today. We continue, and in general, I want you to think about the other point I mentioned. I'll quickly write that down. Yeah, maybe one more point. So for those of you who have figured out the DIY, you can take a step further. See if you can write down. This is going to be vague, but that's okay. Sometimes life is vague. Write down a set of linear equations. You need to define variables. Define variables. Where what you have is a graph G. You have a graph G with vertices E and edges E. Write down, define some variables and write down a system of linear inequalities, and and equations if you like. Of course, every equation is just with inequalities. Right? A equal to B is nothing but A less than equal to B and A greater than equal to B. So whatever. Write down a system of linear inequalities and equations so that all integer solutions where every variable is an integer, also called integral solutions. So write down such that all integer integral solutions to this system. So this system, let's call it star. They should correspond. The important word is correspond. They should correspond to the perfect matching of the graph and vice versa. Correspond to perfect matchings of G and vice versa. Every perfect matching should correspond to an integer solution. Okay, so for this example, if you write down your system, for this example, the number of integer solutions to that system should be exactly k, where k is the number of perfect matchings of the graph. Every perfect matching should correspond to one solution, integral solution, and every integral solution should correspond to a perfect matching. There should be a bijection between these two sets. Yeah? So yeah, anyways, if it is a bit vague, that's okay. This is what I call a TIY. This is not a DIY. This is a TIY. Try it yourself. In other words, it will be discussed in the next lecture. Right? So, but if you can figure it out yourself, you're going to be later. So, anyways, enjoy the weekend working on this and other things. Thank you. Any questions or concerns before we wrap up? Okay, if not, I'll see you on Monday at 5 p.m. Thank you.